I want you to imagine, just for a second, a colony of leafcutter ants.
Okay.
Like if you get down really close, right into the dirt, you see this massive, perfectly choreographed operation. It's essentially a sprawling subterranean agricultural empire.
Right. They're basically tiny farmers.
Exactly. You have these tiny, incredibly specialized insects,
Yeah.
and they're literally farming.
Yeah.
I mean, you have the foragers marching out to harvest very specific pieces of leaves. Then you have the transporters carrying them back.
Yeah.
And down in the dark, you have the cultivators using those leaves to grow a very specific type of fungus for food. Every single ant has a highly specialized role, and the system works flawlessly. And it's entirely in service of the larger colony's survival.
It's a remarkable biological system, and the mechanism behind it is actually fascinating because the colony doesn't survive simply because, one individual forager is exceptionally strong or fast at cutting leaves.
Yeah.
It survives because of chemical communication, pheromones. They create this decentralized network. So if a food source dries up, the network instantly shifts. And if we connect this to the human food system, the metaphor is incredibly striking.
How so?
Well, in our global food network, the individual actors like the commercial farmers, the logistics providers, the agro-industrial processors, they might be highly optimized in their own specific roles. But true resilience depends entirely on how well those disparate parts communicate and coordinate as a single organism.
Which is precisely where we humans tend to hit a wall.
Yeah, we really do.
Welcome to today's deep dive. We are unpacking some incredible insights from Rathika Krishnawamy. She's the Senior Vice President at Findability Sciences.
And her work is just fascinating.
It really is. We're looking at her insights on how artificial intelligence is stepping in to be that vital communication layer, like the ultimate coordinator for our global food systems. And if you are picturing the global food system right now, don't think of it as a smooth, well-oiled machine.
No, absolutely not.
Right. It is a highly fragmented, intensely competitive network of silos. For centuries, every participant has been optimizing their own tiny piece of the puzzle without ever seeing the full picture. So today we're looking at whether AI can finally connect the dots.
And frankly, we are running out of time to figure this out.
Yeah.
Because if we move from the instinctual perfection of that ant colony to the messy reality of the human food system, we are looking at a landscape facing a massive ticking clock. The target established in the research is absolute.
And terrifying.
It is. The world must figure out how to feed 10 billion people by the year 2050.
10 billion. That number is staggering.
Yeah.
And, I mean, we can't just throw more land or more water at the problem because we simply don't have it. We're looking at compounding pressures here.
Right.
Climate change is radically altering growing seasons. We have severe resource constraints, extreme market volatility, rising food safety concerns, and deeply inequitable access to basic nutrition. So the premise here is that traditional decision-making in agriculture is no longer enough to handle these pressures.
That is the core vulnerability. Because traditional decision-making in agriculture and global logistics is inherently reactive.
Reactive, meaning?
Meaning a farmer waits to see if a pest appears before spraying. Or a shipping company waits for a port to back up before rerouting their cargo.
Right, they react to what's already happening.
Exactly. But when you have compounding interconnected crises like, say, a drought hitting at the exact same time a geopolitical conflict blocks a major shipping lane, reactive decision-making just leads to systemic failure. The system must evolve to be predictive.
Let me push back on that a bit, though, or at least try to contextualize it.
Sure.
Because humans have been farming successfully for thousands of years. We built entire civilizations on our ability to look at the sky, test the soil, and know what to plant. It's tempting to say traditional farming has been like driving a car by looking exclusively in the rearview mirror.
Yeah.
But actually, like, a better way to look at it is like playing chess, where you can only see your opponent's previous move.
Oh, that's interesting. Let's follow that.
So if you are playing chess and you only see the previous move, you can still win, right? As long as your opponent plays the exact same conventional opening they've played for 5 generations.
Right. Because you rely on historical pattern.
Exactly. But climate volatility means your opponent is suddenly flipping the board, changing the rules, and playing pieces you've literally never seen before. Traditional, historical knowledge alone can't win that game.
No, it can't.
Predictive AI, on the other hand, acts like a modern chess engine. It's calculating 15 moves ahead based on millions of hidden variables.
That captures the shift perfectly. The historical weather patterns that a family farm or even a massive agribusiness relied on are no longer reliable indicators. I mean, the frost dates are shifting, the monsoon seasons are completely erratic.
Yeah.
So to calculate those 15 moves ahead, we require a massive upgrade in the data we capture and how we process it. Which brings us to how AI operates on the ground, starting at the operational level. Krishnawami's work emphasizes this necessity of what she calls wide data.
Now, we hear big data thrown around constantly in tech spaces, right?
Yeah.
Usually meaning a massive volume of one specific type of information, like millions of user clicks. But wide data is structurally different.
It is. It's about variety and synthesis rather than just sheer volume. An AI system optimizing a modern agricultural operation isn't just ingesting one data stream.
What's it looking at?
Well, it is simultaneously pulling in high-resolution, multispectral satellite imagery to look at crop health,
Okay.
and then it is pulling real-time telemetry from IoT sensors buried deep in the soil that are measuring nitrogen levels and moisture. It is scraping macro weather models, and crucially, it is integrating qualitative historical farmer knowledge.
Okay, this is where my mind immediately goes to the nuts and bolts of it.
Yeah.
How exactly does an algorithm combine qualitative human intuition with quantitative satellite data? Because, I mean, if a farmer says, when the wind smells like dust in late April, the western field usually yields less wheat, that's an intuition based on generational observation.
As
I'm assuming the AI doesn't just replace that intuition, right? It has to translate it. Is it using something like natural language processing to parse through decades of handwritten farm logs or voice notes?
You hit the nail on the head. That's exactly the mechanism.
Right.
It uses natural language processing to digitize and categorize those historical qualitative logs.
Wow.
Yeah. It takes that phrase, dusty wind in late April, and it looks for the underlying data signature. It correlates that historical observation with archival satellite imagery of cloud cover, historical barometric pressure readings, and past soil moisture data from those exact specific dates.
Wait, so it essentially quantifies the gut feeling.
Precisely. It turns the intuition into a weighted variable within a neural network. The AI essentially says, the farmer's dusty wind correlates with a specific microclimate atmospheric pressure drop that always precedes a localized drought.
That is wild.
Right. By synthesizing this wide data, the AI validates and scales that local wisdom. So instead of relying on a human to happen to be outside and notice the wind, the AI detects the pressure drop via sensors and adjusts the automated irrigation system a week before the crop ever experiences stress.
Oh, wow. Yeah.
And this dramatically improves productivity, efficiency, and adaptability.
It builds resilience right from the soil up.
Yes.
But the research is very clear that we aren't just talking about dirt and tractors here, because a massive part of the food system involves agro-industrial environments. The source material dives into a very specific, highly technical example, which I found fascinating.
Sugar mills.
Oh, the sugar mill example is perfect for this.
Right. And honestly, looking at how AI functions inside a massive processing plant is where you really see the power of edge computing and predictive models.
Totally. Because a modern sugar mill is an incredibly complex, high-stakes chemical and physical environment. You are looking at a sequence of intense processes. First, you're milling the raw cane. Then, clarification to remove impurities.
Sounds messy. Very. Then evaporation to concentrate the juice. Then crystallization to form the actual sugar. And finally, centrifugation to separate the crystals from the molasses. And every single one of those stages requires immense amounts of energy. And the timing has to be absolutely flawless.
Right, so a massive, hot, heavy machinery environment. I imagine the latency in human reaction time is the real killer there.
It is the biggest bottleneck.
Because if a human operator is checking a manual gauge every hour, by the time they notice the evaporation chamber is too hot, they've already wasted massive amounts of energy. Or worse, degraded the product.
Exactly.
So how does AI physically optimize that environment? What is the actual mechanism in the middle of all that centrifugation?
So the mechanism relies on IoT sensors and predictive edge computing.
Edge computing meaning it processes locally?
Right. Instead of a human operator relying on a delayed gauge reading, you have sensors inside the evaporators and centrifuges taking hundreds of readings a second. They're measuring viscosity, temperature, moisture content. And the AI model processes that data locally, right there on the edge, without having to send it to a distant cloud server.
Because even a 2-second delay in sending data to the cloud and back could ruin the batch?
Exactly. The AI is detecting microscopic anomalies, fluctuations in the chemistry of the cane juice that a human could literally never see, and then it dynamically recommends or even autonomously executes operating set points.
Give me an example of that.
Okay, so if the AI detects that a specific batch of incoming cane has a slightly higher moisture content because of recent rain on the farm, it instantly adjusts the thermal load of the evaporation chambers by a fraction of a degree to match it.
So it's optimizing the thermodynamics of the plant in real time.
In real time. This prevents bottlenecks, it improves the overall throughput of the mill, and it completely slashes energy consumption.
But let's follow the logical progression here. Let's zoom out.
All right.
Let's say that sugar mill in Brazil hits unprecedented efficiency. The centrifuges are humming, energy use is down, yield is up. That is fantastic for the mill operator. But a perfectly optimized mill or a highly efficient wheat farm is completely useless if the cargo ship carrying that product gets stuck in port,
Right.
or if the people in a distant country who rely on those calories can't safely access them.
Which brings us to the critical pivot in Krishnawami's work. We have to move beyond optimizing individual silos. Because optimizing one farm or one factory does not solve the 10 billion person problem. We have to zoom out to the ecosystem level.
And this is where the challenges become, frankly, exponentially harder.
Oh, without a doubt.
We are talking about ensuring food safety across international borders, global supply chain coordination, targeted nutrition, and early famine detection. These aren't just engineering problems anymore. I mean, you can engineer a better thermal sensor for a sugar mill. You can't just engineer a better global supply chain without dealing with geopolitics, macroeconomics, and, well, human behavior.
They are multi-stakeholder, multi-domain, long-horizon challenges. Consider famine detection, for example.
Yeah, let's look at that.
A famine does not happen overnight, and it is rarely caused by a single factor. It is a slow-moving catastrophe. It's a localized drought combined with a sudden spike in fuel prices, combined with currency inflation, compounded by a breakdown in local transport infrastructure.
So how does AI actually tackle something that impossibly complex? How does it predict a famine rather than just reporting on one after the fact?
It uses something called predictive digital twins. The AI creates a massive dynamic virtual model of the entire global supply chain. It doesn't just look at agricultural data, it ingests economic indicators, shipping manifests, satellite imagery of port congestion, even political stability indexes.
Let's trace a scenario to make this concrete for you listening. Let's say there is a severe drought in Brazil affecting sugar and soybean yields.
Okay, in a traditional model, analysts would look at the Brazilian drought and predict higher prices for those commodities. That's a linear prediction. But the AI digital twin maps the secondary and tertiary effects.
The ripple effects.
Exactly. It sees the drought in Brazil. It knows that because soybeans will be expensive, a massive buyer in the Middle East will substitute with wheat. It cross-references the sudden demand for wheat with the subtle emerging shipping container shortage in the Mediterranean and rising currency inflation in Egypt.
Wow, so it connects the invisible threads.
It does.
It sees that a drought in South America is going to create a critical caloric deficit for millions of people in North Africa, like 6 months down the line.
Yes. It spots the multi-domain pattern long before a human analyst could ever connect those seemingly disparate dots. And it flags the vulnerability in the ecosystem, allowing policymakers and logistics companies to reroute supply chains, secure alternative food sources, or adjust subsidies before the localized shock turns into a regional famine.
Okay, this sounds incredibly powerful, but I have to play devil's advocate here.
Bring it on.
Because we are talking about multi-stakeholder ecosystems. It is very easy to get a brilliant algorithm to spot a pattern when it has access to all the data in a sterile server room. But out in the real world, how on earth do you get fiercely competitive, notoriously secretive multinational corporations and geopolitical actors to actually share the data needed to make that digital twin work?
Yeah, that is the million-dollar question.
Right. If I'm a global shipping conglomerate, I guard my logistics data like it's the nuclear codes. I'm not handing my internal data over to an open AI model for my competitors to see.
You are pointing directly at the biggest hurdle in modern logistics, and it is a reality the research acknowledges openly. The hardest barriers to global food security are no longer technical, they are structural and behavioral. If the AI is starved of data because of corporate secrecy, its predictions are completely useless.
So if the algorithm is ready, but the humans are hoarding the data, how do we solve the human equation?
This is where we see the rise of privacy-preserving AI. and concepts like data trusts and zero-knowledge proofs.
Okay, break those down for me, because that sounds like heavy cryptography. How does a zero-knowledge proof solve the corrupted secrecy problem?
Simply put, a zero-knowledge proof is a cryptographic method that allows one party to prove to another that a statement is true without revealing any of the underlying data that makes it true.
So in the context of the global food supply chain.
In our context, imagine two fiercely competitive shipping giants and a major agribusiness. They won't share their private cargo manifests with each other, ever. But they can all contribute their encrypted data to a decentralized data trust. The AI can be deployed inside that secure environment to scan the encrypted data for supply chain vulnerabilities, like, say, a critical bottleneck forming at a specific port.
Right.
The AI can then alert the ecosystem, saying there is a 90% probability of a catastrophic delay at this node without ever revealing Company A's shipping volumes to Company B.
That is brilliant. The AI essentially becomes a neutral, trusted third party.
Exactly.
It can learn the patterns and secure the ecosystem while keeping the proprietary trade secrets completely hidden. It solves the trust deficit.
It does solve the technical trust deficit, but it still requires human willingness to set up those data trusts in the first place, which leads to the ultimate insight of Vladika Krishnawami's perspective.
Which is?
AI is an enabler. It is not a magic wand. You cannot just sprinkle artificial intelligence over a broken, secretive global food system and expect it to magically feed 10 billion people.
It requires institutions. It requires domain expertise.
Exactly. Real transformation, true resilience at an ecosystem level only happens when data and AI are fundamentally combined with human judgment, shared goals, and collaborative governance.
To me, it feels like AI is essentially the ultimate hyper-advanced dashboard in an airplane.
Oh, I like that.
Like, it can process the altitude, the wind speed, the engine heat, the incoming storm fronts, and it can process millions of data points a second, predicting turbulence before the plane even shakes. But that dashboard still requires a human pilot who understands the overarching mission.
Yes.
It still requires air traffic control, which are our institutions, our data trusts, our shared standards to make sure all the planes in the sky are communicating securely.
Yeah.
And ultimately, it requires human judgment to make the final call on where and how to safely land the plane.
The dashboard is completely useless without the pilot, and the pilot is flying blind in a hurricane without the dashboard. We need shared data standards so different corporate systems can talk to each other securely. We need governance models that incentivize sharing information for the common good, like early famine detection. The algorithm can only optimize the reality we allow it to see, and it can only act on the priorities we set for it.
So it all comes back to us. For you listening, think about the massive journey we just took. We started down in the dirt, looking at the instinctual, perfect coordination of leafcutter ants, where every tiny worker inherently understands their role in the survival of the wider colony.
Right.
And we've zoomed all the way out to the incredibly messy, multi-stakeholder geopolitical undertaking of trying to map the entire globe with predictive digital twins to feed 10 billion human beings by the year 2050.
And that leafcutter ant metaphor really holds its weight all the way through the analysis, because true resilience for the ants and for us isn't about one individual actor optimizing their own silo.
Right, it's not about the fastest ant.
Exactly. It isn't about one farm yielding slightly more wheat or one sugar mill using slightly less energy. It's about the survival of the whole colony. And for humanity, that requires a complete paradigm shift in how we collaborate. We have the predictive AI tools now, we have the wide beta capabilities, we have edge computing. The technology is no longer the bottleneck.
It's the humans.
It is. The lingering question is whether we have the collaborative will to use these tools to secure the entire ecosystem.
Which leaves us with a massive systemic question to ponder as we build this out. If we actually manage to overcome the structural hurdles, if we utilize data trusts and zero-knowledge proofs to build this globally interconnected, AI-optimized food ecosystem where algorithms can predict a caloric deficit 6 months out and instantly reroute global supply chains to prevent it, who ultimately gets to program the underlying priorities of that digital twin?
That is the real question.
When resources are inevitably tight, and a logistical bottleneck forces the algorithm to make a choice about where to route a critical shipment of grain, how do we ensure the system's code values equitable nutrition for everyone and doesn't just automatically default to prioritizing the highest bidder? How we govern these models is just as critical as how we build them.
Absolutely.
The future of food will not be shaped by AI alone, but by how well we connect intelligence, people, and purpose across the entire system. Thank you for joining us on this deep dive. Keep questioning the systems that sustain us, keep looking for the connections, and we will see you next time.